Alrighty. So, the first thing we're going to do today is a little bit of an exploration for the second fundamental theorem of calculus. Yes, there's a second one, all right? It's really not that crazy, all right? It's really not that bad. But there is a second one, all right? So I'm going to kind of lead you through like the very first step here, and then I think I'm going to have you guys kind of go through the remainder of it on your own, all right? So I'll just kind of get you going, all right? Just kind of see what the point is. So we've got, in this case, for number one, we've got a function f of t, which is equal to 2t plus 3. And we are asked to find the integral from 1 to x of 2t plus 3 dt. So we're going to use that first fundamental theorem of calculus, which basically is just how we integrate, how we solve, or how we simplify a definite integral. That's that first fundamental theorem of calculus. It's just what we do when we solve a definite integral. So in order to do this, we need to integrate the 2t plus 3. And so we get 2t squared over 2 plus 3t. And we're going to evaluate that from 1 to x. Okay, which I'm going to cancel the 2's out there. And now when we evaluate, we're going to plug in our upper limit of integration, which is x. So we get x squared plus 3x, that quantity, minus 1 squared plus 3. And if we simplify that, we end up then with x squared plus 3x minus 4. So that is the integral from 1 to x of 2t plus 3 dt right there. Now, letter B, you'll see that very same integral from 1 to x of 2t plus 3 dt inside those square brackets right there, right? But what is this asking us to do? Take the derivative of that thing. We don't need to integrate this again. We already know what that answer is. So we can kind of substitute in the x squared plus 3x minus 4. And so this is really just asking us to take the derivative of x squared plus 3x minus 4. Right? With respect to x, of course, in this case, because it is. Okay. And so when we take the derivative here, what do we end up with? 2x plus 3. Okay? So that is exactly what we're going to have you do. So go ahead, try number 2. Do what number 2 asks you to do. And then you'll see here, do you see a pattern? Use it to find the derivative with respect to x from a to x of j of t dt, where a is a constant. So you can like write that right here if you want to. And then you have 3, a and b as well, and then 4, a and b. You'll notice the limits of integration here are a little bit different, right? So it's from 6 to 2x squared, and from 3 to cosine of x. Kind of funky that our limits of integration are functions themselves. But again, see what you can come up with there. Okay, so give it a try. See if you can kind of figure out what that second fundamental theorem of calculus is going to be. And I'll kind of come around and help too. questions there, right? The one in the middle, do you see a pattern? And the one at the end, do you see a pattern? Both of those are kind of like where you have to summarize what you see going on. Yes. It's either way, because what the order of operations says you can do its inside parentheses first, and then subtract that over the solution, but we can also distribute a minus sign as well. So, yeah, should result in the same thing. One more minute. Are you sure? Okay. Because I know that you said you were packed with stuff. What's that? Okay, well, I just don't want to take away time for stuff that you need to do, for stuff that I don't really need to do. Nice. Yep.
You must be old.
Stickers here too. Yep, just a percent should be fine.
Yeah, I'm just gonna let him solve these two for me.
Just go over those two for you and the question. And the no question. I'm just gonna walk by. Surreptitiously.
Oh wait, yeah.
No. You take this, which is equal to this. So you take the derivative of that. See, you're taking the derivative of this integral. What is this integral equal to? Well, you have this integral, right? Equal to this. You took the derivative twice. You took the derivative of this and put that here. And then again.
Sarah's sandwich.
You just take the derivative of this.
I like this.
In fact, you don't need to integrate. You don't need to integrate. You're just taking the derivative. Just take the derivative of this. You can factor if you want to. If you go and take the derivative of this, you're going to use the product. So, why make it harder?
What'd you get for the last one?
I'm just too smart.
You get ahead of yourself, I guess, yes.
Still pretty better than
Yes.
I just want to make sure that I could just cross that.
what you're doing.
Yes, so then the derivative of that, yes, find the derivative of that.
I like this unit.
Okay.
Okay, I'm not sure.
Okay, so here's the top. All right, we at least should have gotten to this point, for sure, right? Okay. So, keep in mind here, right, that minus 15, which is that what we get from, our 27 minus 27 plus 15, when you take the derivative of that, it's a constant, so the derivative constant is 0, so it goes away, right? The lower limit of integration essentially all goes away. Do you see a pattern? Use it to find the derivative with respect to x of the integral from a to x of j of t dt, where a is a constant. So what will this thing equal? J of x, exactly right. And that's it. Yes?
Why did we not add a constant for, like, 1a, like, plus c?
It's not necessary, right? We showed that yesterday with the definite integral for the fundamental theorem of calculus. Where did I show that? I think in the very first page, actually. When you integrate, you could put the limit of integration in there, but then when you plug in your upper and lower limits, they both have a plus c, and so the c's are going to cancel. So we don't bother writing it. Okay, for indefinite integrals, though, for sure, put the plus c, right? But because they're going to cancel, you don't have to write it. Okay. All right, so anyways, back to there. So yes, this is kind of like the summary thing here. Okay, now hopefully this should make sense, right? Because what are we doing? We're integrating a function from a to x there, and then we take its derivative. So if you integrate something and take its derivative, it's like you do something, and then you kind of undo it in a sense, and you end up back at the original function, except because we integrated with respect to t, but then we plugged in an x, we're now in terms of x and not t, right? We plugged it in, so it changed the variables, but that's it. That's it. Okay, a is a constant, right? That lower limit integration, it disappears when you take its derivative. Right? So then when you go down to number 3 and 4, similar behaviors occur, right? We've got for k of t equal to cosine t, we end up evaluating sine of t from 6 to 2x squared, which becomes sine of 2x squared minus sine of 6. Sine of 6, what is that? It is a constant, right? We don't know what the value is, but when you go to take its derivative, it's going to disappear because it's a constant, right? Sine of a number, its value, it is a constant. So it disappears when you take its derivative because it's 0. When the derivative of constant is 0. And so we end up with then just taking the derivative of this. When we take the derivative of this, what do we have to use? Chain rule. So outside is cosine, leave what's inside alone, times the derivative of what's inside. So cosine of 2x squared times 4x, or 4x cosine 2x squared. Right? Likewise down here. E to the t, that's easiest integral of my life, e to the t. Okay? And then we evaluate from 3 to cosine of x. So you plug in the e to cosine x minus e to the 3. Okay? Again, what is e to the 3? Constant. So its derivative will be 0. So we end up with just taking the derivative of e to the cosine x. Again, chain rule applies. The derivative of e to the something is e to that something times the derivative of something, negative sine of x. So you get this. So then, do you see another pattern? Use it to find this. So what will the derivative with respect to x of the integral from a to g of x of f of t dt, what will that be? F of g of x times g prime of x. Very good. Okay. That is the second fundamental theorem of calculus. That is the second fundamental theorem of calculus. Right there on the next page. Okay, so theorem, the second fundamental theorem of calculus. If f is continuous on an open interval, then for every x in the interval, the derivative with respect to x of the integral from a to u of f of t dt equals f of u times u prime minus f of a times a prime. Notice in this case, we are not specifying that a or u are constants, right? In the previous step, we were always assuming that a was a constant. But in fact, a does not need to be a constant in order for us to do this. So a could be a function, u could be a function here. When you evaluate this, you evaluate u in the original function here, because again, the derivative and the integral kind of cancel out. You evaluate u in the original function, and then you multiply by the chain rule times the derivative of u, minus the lower limit, f of a, times a prime. So notice we don't actually end up taking the integral here. You can kind of skip over that step. So if we look at a problem like this, okay, and apply it here, so the 3 here is like that a, the 3x minus 2 is like u. Okay, and so when we apply the second fundamental theorem of calculus here, because we're taking the derivative of an integral, we're going to just evaluate 3x minus 2, or the u in for t squared. So it's going to equal 3x minus 2 squared times u prime. What's u prime in this case? 3, right? Times 3. So there's our f of u times u prime minus, we're going to evaluate a. 3 squared. What's a prime? 0. So f of a times a prime. So your lower limit of integration disappears, right? It's just 0. And so we end up with 3 times 3x minus 2 quantity squared. Okay. That's all there is to it. Yes?
Is it like multiply that by 0?
No, I think you can get away without having to do that, yeah. I'm just showing it now because, you know, we're too smart at it, so. But yeah, good question. I don't think that's necessary. Yep. You're welcome. Right? Questions on any of that? Any other questions on that? So these are not that bad then, right? So if we look here at the next function, okay, we're told to find the derivative. Now here's a little bit of a strange thing. Find the derivative of this function, but the function is an integral, right? F of x equals the integral from x to x cubed cosine of t dt. So for example, just to kind of like back up one step here before we actually do what the question's asking. If I wanted to find capital F of 1 here, where would that 1 plug in here? Where does it plug into this function? Not for nowhere, and for the x's. The limits of integration. The limits of integration there. Because if we're replacing x with 1, that means we're saying our x is 1. So the x here would be a 1, the x here would be a 1. So we'd integrate from 1 to 1 of cosine of t. And what's the integral from 1 to 1 of anything? 0, right? Because you've got no area there that you're accumulating. All right? So anyway, we're going to find the derivative of this, though. So capital F prime of x equals, so we're taking the derivative of an integral. Second fundamental theorem of calculus. That's what we're going to use here. Okay? So we just have cosine of the upper limit, okay, times the u prime, or the derivative of the upper limit, so 3x squared, minus, bless you, cosine of the lower limit times the derivative of it. And what's the derivative of x? 1. So we end up with 3x squared cosine of x cubed minus cosine x. And that's our derivative. Okay. So far, so good? Okay. This could be like one of those situations where it's so simple that it's complicated, maybe, but anyway, let's try this one now. Okay, f prime of x equals, again, we're taking the derivative of this integral, right? If we're taking the derivative of this side, we're going to take the derivative of this side, derivative of an integral. So now our upper limit is 6. So we're going to plug that 6 in. So it'll be 3 times parentheses 6 plus 7. So that's our function there. There's f of, u. That's our u. And that's our a there. F of u right there times, we now need to multiply by u prime. What's the derivative of our u here? 0. So this sign gets multiplied by 0. Oops. Plus, oops, not plus, goodness, minus, upper limit minus lower limit there. All right, sine of 3 parentheses 2x minus 1 plus 7. Okay, so there's our f of a times, now a prime. What's the derivative of a here?
6.
What is a? 2x minus 1, so what's a prime? 2. Yeah, be careful there. And that's why this problem is written this way. Okay, is to be careful about whose derivative you're taking here. It's the limit, the lower limit's derivative in the specific case. Okay, the lower limit's derivative in this specific case. So again, we could stop here if we wanted to, but of course that's going to be 0 minus 2 sine of, let's see here, 6x minus 3, but plus 7, so plus 4. Okay, so you can just kind of circle that piece right there. Okie dokie. All right, so why don't you guys go ahead and try number 10, multiple choice. AP style question there for you. Okay. F of x is an integral from 1 to x cubed of 1 over 1 plus ln t dt. Find f prime of 2. Find f prime of 2. So my recommendation, find f prime of x first, then plug in 2. Okay? I would suggest against trying to do it all at once. I mean, you can probably do it, but... multiply by that, the derivative of the lower limit there, or the upper limit. So it should be times then a 3x squared. I see what you 3x squared is what you got over there. And that's just a 3. So what is the derivative of x cubed? 3x. There you go. Okay, so you're going to substitute again your lower and upper limit because you're taking the derivative of this integral, right? This is f. You want to find f prime, so you get the derivative of this. How to do that is you're just going to plug your upper limit into the function, the integrand, and plug the lower limit into the function.
It's so much more work.
Yes, you did. You did. Yep. There you go.
It's been a day. I'm sorry.
It's been a day.
You need a sandwich.
Put some mayonnaise, lettuce, tomatoes,
I
lunch
know a
meat.
sandwich will make everything slightly better.
I
It is
100%
my
agree with
theory.
that. That is good.
Everything is wrong. Slightly better. A sandwich.
Although women would have to be making this.
Alright, well my theory is
I always say that I 100% agree with it, except for one small thing. Women would have to be making sandwiches. That's right. If I have a chance to put in a sexist comment, usually I do. I have to take those opportunities.
And the answer is letter D, okay?
I'm not.
Questions on that at all? I remember really liking these second fundamental thermic calculus problems when I was in calculus. But I'm a math teacher, so I don't know if that's just me. Okay, so, yes, nerd indeed. All right, so let's take a look here at number 11. All right. First things first, here we want to evaluate f of 1. So we've got our function, and we want to evaluate it at 1. So where's this 1 going to go in this function here? Into the x, right? So x is being replaced by 1, so it goes right up there. So it's going to be the integral from 2 to 2 times 1, which is 2 of 3t squared minus 5 dt. And so this is 0, right? From 2 to 2, right? There's no space between that, right? We can't accumulate any area there if you want to think about it in terms of the area, right? We're integrating from 2 to 2 equals 0, okay? All right. Next, f prime of 1. Okay, so that means we need to find f prime of x first, so I'll do that. Okay, so we're taking the derivative of an integral. So this is an application of the second fundamental theorem of calculus. We're going to have 3 parentheses 2x squared minus 5 times 2. Notice where I put the times 2. Look at where I put that times 2, the u prime there. Okay, it is multiplied by the entire integrand. Okay, because it is f of u, which is this, times u prime, like that. Okay, so we have to multiply the entire integrand by that 2. Okay, the entire integrand gets multiplied by that 2. And then minus, and of course this one's going to be 0, but I'll go ahead and write it out just because, okay, I like to make things really packed in there. All right, so our lower limit disappears, right? Minus f of a times a prime. And so let's see here, we get, what did 24x squared minus 10?
Yep.
Okay, and so then we're going to evaluate, of course, f. We're not done yet, right? We want to find f prime of 1. And so it's going to be 24 times 1 squared minus 10, which is then 14. Question? $24? 2x squared becomes 4x squared. 4x squared times 3 is 12x squared times a 2 gives you 24x squared. Okay, and then finally letter C, f prime prime of 1. what do we do now? Well, what is f prime prime going to be? What's f prime prime of x? The derivative of f prime, which is right here. So it's just going to be 48x.
Oh.
That's it. We're just taking the derivative of that thing. Okay, and so then f prime prime of 1, 48. Now, let's go way back to like unit 3 or I guess unit 3. I think that's where we learned it. Or unit 4 maybe. Maybe unit 4. Anyway, f of 1 equaling 0, okay, what does that mean? Okay, so we're talking about the point at 1, 0 on f of x, dot, dot, dot. All right, what's happening? F prime of 1 equals positive 14 means what is happening about f? The function is increasing at 1. And concave up, exactly right. Whoops. X is increasing, sorry, f is increasing at x equals 1 because f prime of 1 is greater than 0. F is concave up at x equals 1 because f prime is greater, oh, f prime prime of 1, I guess I'll say. Okay, so all these things, right, still apply, right? We can still use these analyses to answer some questions. Okay, so speaking about functions being defined by integrals, that's our next topic. All right. So let f of x equal the integral from -1 to x of f of t dt, and x is between -1 and 4. X is between -1 and 4, where f is the function graphed. Okay, so letter A asks us to complete the table of values for f, capital F. So let's be really careful here. We are completing a table for capital F of x. Capital F of x is defined as the integral from -1 to x of lowercase f of t dt. What do we know about lowercase f? We have its graph right here. This is the graph of lowercase f here. Okay? So when I evaluate the capital F at -1, that means I'm going to do the integral from -1 to -1 of this function right here. What's that answer going to be? 0, because we're integrating from -1 to -1, so that's going to be 0. That's an easy one to do, right? No problem. All right. For the next x value, we're evaluating x equals 0. That means we're going to integrate lowercase f here from -1 to 0. How can we use this graph to help us evaluate the integral from -1 to 0? So -1 and 0, here's our space right there. What do we need to do to find the value of this integral? What does the area? It's the area of the region there. Okay, it's the area. All right. So we want to find the area of this region from -1 to 0. Okay. Sometimes my brain can only handle so many things, I guess. So anyway, from -1 to 0. So we want to find this trapezoidal, area. So yeah, it's 1.5, right? You can count it too. I guess you can see there's 1 block. There's half a block, so it is 3 halves. Okay?
I can count squares.
You can also use trapezoidal area formula, right? 1/2 base 1 plus base 2, so base 1 is 1 plus base 2 is 2, so 3. The height is 1, so 3 still. Half of that is 3 halves. All right, now for 1. All right, so we're going to integrate, again, to evaluate at x equals 1, we're going to integrate from -1 to 1. So that means from -1 to 1, we're now going to get this region right here. Okay, we're going to evaluate this area, which is another trapezoid. Okay, the base here is 1 plus the other base of 3, so 4 divided by 2 is 2 times the height of 2, so 4 total is our area there. Okay, you can also count the squares. 1, 2, 3 squares, and 2 halves of a square, 4 squares. That's easy because they're nice half squares there for us for that slope. I know they look like rectangles, but it's just the, I I don't know, the way the scale of the drawing there, it makes them look like rectangles, but they're really squares, square units. All right, so we can keep going here. So why don't you guys go ahead and keep going, fill in the rest of those, 2, 3, and 4. Okay, 2, 3, and 4. So we continue to add on those areas. Remember, you're always integrating from -1 outward. So at 2, you're going to have to include the area of this trapezoid, right, from -1 to 1, but they're going to add on the area of this trapezoid right here. Okay, so proceed from there.
Looking good there, Steve. Good job. So far, so good.
1/2 parentheses base 1 plus base 2. So if you don't have the same, you're gonna try it. Good.
He's arguing with me.
Do the area of the triangle and do the area of the trapezoid.
Is right.
What triangle?
This right here is a trapezoid. Right here is a trapezoid, correct? This is a triangle.
Well, that's 2. Well, it's unequal. It's 2.5. It's 1/2 base times 2. What's 2.5? What's half of 5? 2.5 times 2. Oh! Yeah, that's 2.5.
How do you do 4? Well, so
How did you get to this?
Good question.
that area.
Hey, I got the 4th one right though.
And then below the x-axis we would count it as
I don't know, the number that says 4, Carter?
okay. All right. So, I got the table almost finished here, but I didn't answer number 4, right? So we get up to 3, which is this region right here, right? All this together, right? Up to 3 gives us a total area of 7. So this like odd shape right here from -1 to 3 is a total area of 7. What can we do though? What do we have to do with 4? When our graph goes below the x-axis and we find this area, what should we do? Subtract it, right? We count it as a negative area or negative region. And by symmetry here, you can actually see from 2 to 3, right, that positive area is precisely the 3 to 4's negative area, so they're going to cancel out, take us right back to what it was at 2, which is 6.25, or 25/4. Okay, so you can use symmetry to your advantage here to kind of help you figure things out. Sean? Correct. Yep. All right, so now the next thing it asks us to do is to sketch a graph of f, and we'll sketch that graph right on our axes here. So we have our points, right? We have the point -1, 0. So -1, 0, we have a point right there, okay, on the x-axis. Then 0, 3/2, we'll have to kind of eyeball that one, but roughly right there. 1, 4. 2, 6.25. 3, 7. And 4, 6.25. Okay, and so we can connect these dots to kind of give us, again, just that's a possible sketch, or possible, answer here. Like that. Okay, so there's capital F. Capital F of x. All right. So, where do you notice the capital F of x is increasing? For what intervals? from -1 to 3, right? You can see it going up from left to right from -1 to 3. What do you notice about the behavior of lowercase f from -1 to 3? It's positive. Oh my gosh, because lowercase f is the derivative of capital F. So where the derivative, or lowercase f, is positive, capital F will be increasing. And then when lowercase f is negative, capital F is decreasing. Okay, you see that? Isn't that crazy? So f, capital F, is increasing from -1 less than x less than 3 because... And I like to write this. I think this is maybe a safer way to write it because f prime of x equal to f of x. Okay, I like to establish that these are the same thing. Okay, is positive on this interval. I don't know. I do this because I'm not sure if just saying because f of x is positive on this interval because we're talking about capital F. But we're using lowercase f. I think it's important to establish that capital F prime is f. So then we can say, you were essentially saying this is positive because this is positive, right? And so therefore capital F will be increasing. So I think it's important to put this way. Yes, Sean.
So if they asked us this question, they were talking about, like they had us sketch the graph of f. We just say we graph f and it was positive.
I see what you're saying there. I mean, I think you, I don't know. I prefer this. I mean, just, I don't know. I think this is to me just in case. So, could it be okay? Potentially, I don't know, but just in case. All right, turn the page here. Okay, we're going to go through example 13, and then we're done. Okay, we're not going to go up to the theorem of net change. But we only have 10 minutes left, so, or less than 10 minutes left, so sorry about that, guys. It's a little packed. We did do a lot of stuff in the front of the class today, though, too, so, at the beginning of class, I should say. Okay, so, let capital A of x equal the integral from -3 to x of f of t dt for x between -3 and 4, where f is graphed. So there's lowercase f, and we're trying to talk about capital A. Which is larger, a of -1 or a of 1? Justify. Okay? So what do we say here is going to be a greater value? A of -1 or a of 1? Well, let's look at our description for A. A is the integral from -3 to x of f of t. So for the a of -1, we're going to integrate from -3 to -1 here. From -3 to -1, which would yield this area. Right here, right? This area right here. Whereas a of 1 will be integrating from -3 to +1, which will yield this area right here, which will be greater. A of 1, right? Because we're accumulating more positive area there. Okay, a of 1. And again, for my justification, here's what I'm going to say. Because a of 1 accumulates more positive area over -3 less than x less than 1 than DHAN a of -1 over -3 less than x less than -1. Okay. I don't know. I think it's sufficient. I think it's pretty sufficient there. Okay, I think it kind of covers, because it gives a good enough description. Okay, so you could, if there's a more succinct way of saying it, there might be. I don't know, but that's what I would say there. Okay, so if you can remember back to when we were doing. Oh, sorry, Gabe.
So I'm so confused on what you're trying to find. Like, why is it larger?
Because this is f. A is the integral of f from -3 up to whatever particular x value we want. So if this is f and we're integrating for a of -1, that means we're going to integrate this function. We're going to find the area under the curve and above the, or between the curve and the x-axis from -3 to -1. So that's like this region right here. Okay? So that would be some value. But then if we integrate from -3 to +1, we're going to include that area of a, but then also add on this region as well, right? So bigger, greater, because it's also above the x-axis, so that's going to be a positive value, right? Okay. Now, next question. Which is larger, A of 2 or A of 4? Good, A of 2. What's the reasoning there?
More negative area under 4.
Right, less negative area, right? So A of 2, again, starts at negative 3, accumulates all this positive area up to 1, but then A of 2 has this small negative region that's going to cancel out some of this positive area. However, for A of 4, we're going to include all this positive region again. We're going to include this negative area up to 2, and then include additional negative area up to 4. And so A of 2 is going to be greater. Okay, and again, I don't necessarily have a great succinct justification here, but I've got something that I think is pretty decent. So because both A of 2 and A of 4 accumulate equal positive area from 3 less than x less than 1, but A of 2 accumulates less negative area over 1 less than x less than 2 than A of 4 over 1 less than x less than 4. Again, is it succinct? No. Could there be a better way to do it? Maybe, but I think that covers all the bases at least. Okay, I think that kind of like gives a good enough description there. Okay, this kind of justification is something that you will need to be able to produce. Okay, this is a very common kind of free response question on the AP test. Okay, so just keep that in mind. All right, letter C. Where is A increasing? Well, what would we expect here? So when we want to determine when a function is increasing, what do we normally look at? If we want to know when a function is increasing, what do we normally look at? It's what? The derivative of it, right? What is the derivative of A? It's going to be f of x, the function here. This is the graph of the derivative of A, right here. Okay, that's A prime. Okay, right? A prime of x is f of x, right? Because you're going to plug the x in there, f of x, multiplied by the derivative of x, which is 1. I guess I could do it this way. And then minus f of negative 3, but times 0, right? That's that second fundamental theorem of calculus. So A prime of x is really just f of x. Okay? So, according to this graph here, where will A be increasing? From negative 3 to 1 because... And so I'm going to say A is increasing negative 3 less than x less than 1 because A prime of x, which is equal to lowercase f of x, is positive on this interval. Okay, lastly, does A have a relative minimum, relative maximum, or neither at x equals 1? Relative maximum because it changes from positive to negative. So A has a relative maximum. Do not abbreviate max, put maximum at x equals 1 because A prime of x equal to f of x changes from positive to negative. No plus and minus signs. At this point. We made it. Oops, I'm off the screen. There we go. Okay. All right. Okay. So your homework is posted to Google Classroom. Okay. I think it should have problem set 3 posted too. Yeah, it should. Yes. So set requests. I'll take those here. So okay, Urza. Okay. Ariana. CC. Yes, Celia, you got it. Other set requests, Emily, Ella too. All right, Madison, you got it. Cassie, you and the crew.
Yes, and I wrote the thing, but there's like one thing that I don't know how to phrase, and I don't know how to wrap it up.
Okay, we can talk.
Yeah, and like edit.
Did you want to do lunch again then?
We can.
Okay.
Or I can like have you like read it and then like during like that while I like do other stuff and then like
That's
edit
fine.
it and then like fix it during lunch.
Yeah, that's fine. That's up to you. Whatever you want to do. I can do whatever. Any other set requests? Alrighty, folks. Have a good day. See you tomorrow. Scoot through here real quick. Go ahead there. Oh, thank you.
Are we ever gonna figure out how to like solve that if both of them have variables in it, like a and b?
Yes, I would like the function there. You mean?
Yeah.
Yeah, we did one.
No, like for all of that, like when they're asking if A2 or A4 is larger.